We've met the Arrhenius definition of acids and bases, and under Arrhenius we said an acid is something that makes H plus or H3O plus ions, and the Arrhenius definition of a base is something that makes OH minus ions in solution. There's another definition of acids and bases called the Bronsted definition, and I believe sometimes the O has a little slash through it and the E has a little umlaut above it, but we don't have to write it like that if you don't want to, although don't tell Bronsted's mom, I'm sure she'd be disappointed. And under the Bronsted definition, we define an acid as something that can give up H plus ions. So an acid is an H plus donor, which is very similar to Arrhenius, but the big difference is a base is something that can actually accept those H pluses. And so it becomes just really a game of catch. And so in class, I normally like to go ahead and bring a magic 8-ball and ask people to kind of play a game where they pass the magic 8-ball backwards and forwards. And these people look very, very happy here. And so the reason for that is that if the person on the left has the H plus and the person on the right doesn't, so if we look at this molecule here with the H plus ion, and I'm not sure I can make that any bigger, but maybe I'll make it a lightsaber or something. So they are like an acid. They can give it to the other person, and if they give it to the other person behaves like a base because they accept it. Now the really cool thing is, right, and this would be really cool with lightsabers, but if the other thing has the H plus now because it was a base, and the other thing doesn't, then it can actually flip around and act like an acid now, in the sense that it can give it back to where it started. And so we have what we call these conjugate acid-base pairs, where they essentially can throw a proton backwards and forwards to each other. And it's kind of neat, where one thing acts like an acid and it gives it to the other thing, which means it's a base. And once the other thing has it, it can say, well, I don't really want it anymore. And it can act like the acid, and it can throw it back. So let's go ahead and look at my favorite acid again, which is acetic acid. And I'm going to draw my acidic hydrogen up front, but I'm also going to color it in red. And so here's my acetic acid, and I'm going to let it react with water. It's going to be in equilibrium, and the equilibrium arrow I'm actually going to draw smaller going forwards because it's only a small percent that actually does this. But essentially, you just have to watch that proton. So that proton is going to be thrown to the water molecule. And if it's going to be thrown to the water molecule, that makes this the acid, and it makes the catcher of the proton a base. And on the other side, right, the acid has lost its proton, so I'm going to write C2H3O2 because the proton has a positive charge. I can go ahead and write that above the arrow there. It leaves behind a negative charge there, so that is technically an anion. And the H2O has gained a hydrogen, so it is H3O plus. Unfortunately, I can only write the one red in H. And it gained an H plus, so there we go, H3O plus. And this proton can actually go in the back direction as well. So just like the game of catch we played there, let me go ahead and use a little red dot again. So the proton went over there to the water. It turned the water into the hydronium ion. The hydronium ion can pass it back. And I'll draw this on the underside here. Excuse me, a hiccup in here. So it can pass it back. And remember, the equilibrium means it can go in both directions. And if it passes back, the H3O plus becomes H2O. It lost the plus, so it's H2O. So there's your water. And of course, if the acetate ion gained H plus, then it becomes acetic acid. So the H plus goes up front, and there we go over there. So on the other side, we can write the H3O plus as behaving like the acid. And the C2H3O2 minus, because it's accepting the proton, is behaving like a base. And if you notice, we've got some pairs here. So over here on the left-hand side, we've got our acetic acid, and it's an acid when it's got the proton. And on the other side, it's the acetate ion, and because it doesn't have the proton anymore, it can catch the proton, which means it behaves like a base. And if we look at the water, we can see over here on the left-hand side, the water is behaving like a base because it can accept a proton. But on the other side, the hydronium ion is behaving like an acid because it can give up a proton. And so these are called conjugate acid-base pairs. And we're always going to see sort of a pair of pairs here. So this is a conjugate AB pair. That's my sloppy notation here. And if you notice, they only differ by a proton. So they differ by a proton. So it's just a game of proton catch. If you've got one more proton, then you are called the acid, because you can throw it. And if you've got one fewer proton, right, or one less proton, I suppose, then you are the base, because you can catch another proton. So we can always see these acid-base conjugate pairs here. So here we've got one fewer proton, one greater proton, one more proton, so that's the base acid pair. And here we've got the acetic acid with the extra H+, the acetic acid after losing the H+, right, the acetate ion. And so this is our second pair here. So we've always got these pairs of acids and bases. And it really just stems from this game of catch, where you've got this pair of molecules that can throw the proton backwards and forwards. And the pair is either it has the H+ in the acid form, or it's lost it, the base form. And again, over here, when it's got the H+, it's the acid form. And when it's lost the H+, it's the base form.